Hi all, and welcome to the Emergent Vision Technologies presentation. I am John Ilett, President, CTO, and company founder, and I look to provide details of how Emergent supports performance line scan imaging applications from start to finish. As everyone would know by now, Emergent has pioneered 10 GigE, 25 GigE, and 100 GigE camera development. We are not your typical camera company, but rather make it our responsibility to make the technology accessible to all, which means providing the appropriate tools like optimized software, third-party component validation, and even turnkey and consulting services so our customers can hit the ground running in high-speed and high-performance imaging. Here's a quick snapshot of the adoption of GigE Vision products ranging in speeds from 10 GigE up to 100 GigE. Emergent has shown how top performance can be achieved and opened up many markets, including machine vision and entertainment, to the use of such technologies. Some companies are just now leveraging our efforts towards releasing 25 GigE and higher speed product, but still a ways to go to provide ratified, mature, and performance product. For line scan, the products range from 4K at 172 kHz up to 16K at 500 kHz, with a special nod to 8K TDI at 1 MHz line rate and 16K TDI at 500 kHz line rate. For line scan, Emergent is now shipping cameras supporting 8K TDI at 1 MHz line rate and 16K TDI at 500 kHz line rate, which are a big hit for applications like battery inspection or other line scan applications needing high line rates with lower lighting requirements. Here we will provide a snapshot of the features for one of Emergent's popular models in battery inspection. Based on the G-Pixel GL5016 sensor, this 16K model hits the sensor's max line rate of 400 kHz by utilizing the Emergent pioneered 100 GigE interface. Other highlights include a wide -20°C to 50°C temperature range, a 3-year warranty, fanless operation or fanless options, lowest power of 18 watts, smallest size, modular QSFP28 transceiver options, flexible I/O options, full-featured line scan features such as encoder, flat field, and spatial correction, and of course zero copy and GPUDirect technologies. As we will see, it is not just about the camera alone, but the complete software and support package that further sets Emergent apart. Here we are streaming and processing a 16K 400 kHz line scan image. This computer is using an NVIDIA RTX A5000, and we are streaming images via GPUDirect to this GPU, where a simple custom brightness plugin has been instantiated. The output is currently just being piped to a display task so we can see the raw and processed images in the live view. Similarly here, we are streaming and processing an 8K 1 MHz TDI line scan image. We increase the TDI stages used here to show the expected intensity improvement. As we have seen, our software and systems expertise allows you to scale system processing to meet the requirements for higher performance applications like this. This animation illustrates a typical task of an area scan camera, which is inspecting objects on a production line. The cameras here are hardware triggered by the sensor looking for objects on the conveyor. Images are transmitted with low latency and jitter back to the computer for analysis and action. Generally, the object under inspection is captured fully in a single image. Emergent area scan cameras have 3 inputs and 3 outputs with opto-isolated and TTL options depending on your application needs. This animation illustrates the same task with a line scan camera. Generally, line scan cameras are used for scanning a continuous web of material like print or fabric, but does not preclude applications as shown here with discrete objects. The cameras here are hardware triggered by the sensor looking for objects on the conveyor. The individual lines of a given frame are triggered synchronously through the use of the continuous encoder signal shown in green. The lines of a given image are immediately transmitted back to the computer and assembled in the user buffer with zero copy technology. Emergent line scan cameras have encoder RS422A/B inputs, 1 trigger input and 2 outputs. TDI line scan cameras are used to expose the same line on the object multiple times to allow either higher speeds with the same lighting or same speed with lower lighting brightness requirements. TDI achieves this by having multiple lines in the sensor with each line exposing multiple times, and the exposure or line rate is perfectly synchronized to the movement of the conveyor through the use of the encoder. We will now review the Emergent line scan camera implementation details alongside of some line scan fundamentals, starting with the I/O connector of the cameras, which is a 12-pin connector featuring differential quadrature encoder inputs as well as other general purpose inputs and outputs. Here we see the general block diagram of the triggering options of the line scan cameras. Many modes are supported, which vary from full internal based triggering to full encoder based triggering for precise synchronization with moving conveyor systems. Here we see a subset of camera parameters specific to line scan camera operation, which fall into categories such as general purpose, image calibration, color calibration, external trigger control, encoder statistics, and specialized. A line scan fundamental is dark and lit FPN calibration, which falls under our image calibration category. On the left, we see contrast enhanced dark images before and after dark FPN calibration. On the right, we see lit images before and after lit FPN calibration. The graphs shown illustrate column averages, which highlight the superb correction that the camera performs with a single click. The calibration curves can be saved and loaded to eliminate the need to recalibrate when powering up the system. Our line scan cameras support quadrature encoder A and B inputs, which allow the camera firmware to detect forward and backward motion by tracking the 4 encoder phases. With mode D configured as shown, we can set the GP encoder direction parameter to allow filtering in of only forward or backward pulses. Additional camera firmware encoder features include an encoder pulse multiplier and an encoder pulse divider, which are used to synchronize the material movement with the line triggers, which can vary based on encoder model and magnification, for example. We also provide statistics counters to allow system integrators to validate the triggers post multiplier and divider to check trigger rate and jitter characteristics. A fundamental exercise in line scan systems is to configure the scan rate to create the correct aspect ratio of the pixel. In mode A, which is an all-internal triggering method, we use the line time parameter and simply adjust the line time until the approximately correct height and width aspect ratio is observed. We can calculate this as well, of course. Note that this line time parameter does not track changes in material speed, so the user must take care of this if correct image proportions are desired. In mode D, which is an all-encoder triggering method, we need to set the encoder divider to the appropriate value to correct image proportions. This method is popular since it does track material speed without any runtime adjustments. Unlike color area scan sensors, which typically use a tight 2x2 Bayer pattern and a debayering process involving approximation through interpolation, color line scan sensors such as the one shown here have a much greater separation in the red, green, and blue channels. Every encoder cycle generates one exposure for all RGB pixels at the same instant, but these pixels are looking at different parts of the material. We need to buffer red lines and wait 4 encoder cycles before the green exposure of the same point on the material. Similarly, we wait 4 encoder cycles more before the blue exposure of the same point on the material, before finally outputting the complete RGB pixel. The G-Pixel GL5016 16K 5 micron 400 kHz line scan sensor, which we ship in the Emergent Pinnacle LZ 16K G5 100 GigE line scan camera, has special capabilities to output arbitrary rows of the 16-row sensor for specialized operations. More commonly, this is used for color imaging as shown on the right, where we grab one red, one green, and one blue line, and then simply employ spatial correction as previously shown, as well as employing color calibration using the camera's white balance and color correction matrix features to create a best-in-class color image scan. We note that this trilinear operation, that there is no approximation through interpolation like color area scan bare cameras, so the color reproduction is optimal. A new and exciting NVIDIA computer has hit the market in the DGX Spark, which is a fully integrated computer with built-in GPU and even a built-in dual-port ConnectX-7 NIC. Any Emergent camera can plug directly into this unit and gains immediate access to the powerful NVIDIA Blackwell GPU via zero-copy and GPUDirect access. And no, these QSFP28 ports or other NIC ports are not compatible with CXP over fiber nor CameraLink HS cameras, which have opted to adopt the Ethernet physical layer from the IEEE. For these protocols, expensive adapters would be required to bridge to NVIDIA product. As we have seen many times before, Emergent has full support of NVIDIA GPUs, which seems to be increasing in performance at a phenomenal rate. Here we have provided zero copy and GPUDirect for over 7 years on Windows and Linux. As part of our validation process, we test and fully qualify a number of such off-the-shelf cards from our primary vendors Broadcom and NVIDIA Mellanox, where both Linux and Windows are supported. We do remind that Emergent's own FPGA-based NIC grabber hybrids remain available for those looking for truly long-term support and additional FPGA-specific features, and/or front panel trigger akin to traditional frame grabbers. I note that Emergent NICs now have full GPUDirect support on both Linux and Windows. I also need to note that while some claim to have or are working on GPUDirect for both Linux and Windows, it is strongly advised to see proof of true GPUDirect. There are a few tools to view the system memory bandwidth utilization. It's not to be confused with capacity utilization. And a GPUDirect implementation should not have any utilization on the bandwidth side of your system memory. Also, be very wary of those promising or working on such development, but rather insist on having this up front before committing to any vendor. Our eSDK is a fully featured and very powerful SDK, which has formed the basis of some impressive applications over the past decade. eCapture Pro is built on top of this SDK and is a UI-based program which allows rapid prototyping of performance multi-camera applications using GPUs or other processing resources via our plugin functionality. We now introduce our eSDK Pro, which is also focused on performance multi-camera systems, but now allows developers to write a very small fraction of the code required by typical SDKs in order to complete the application for a far simpler integration and quicker time to market. Here we show how easy it is to integrate third-party devices into your eCapture Pro or eSDK Pro application via our plugin API. Opto Engineering provides LED pattern projectors. Advantech provides generic I/O cards, and we will use this card to trigger the LED. Zaber provides encoder-based rotary stages, and this stage will be used to rotate the PCBs on the turntable and to trigger the camera. The stage will provide triggers to the camera as a PCB is present. The camera will provide images via network card and GPUDirect to the NVIDIA GPU, where defects are detected using an unsupervised deep learning approach, and an action is taken by turning the LED on to illuminate the defective part with a red X pattern. To set this system up, we simply create a small plugin for each of the third-party devices and then instantiate them in either eCapture Pro or using eSDK Pro. Here is a short video of the physical setup showing the turntable, illumination, LED, and the Emergent Aros 10 GigE camera. An overhead shot of the turntable highlights the need for machine vision techniques on this repeating very high-speed 8 PCB array setup. In the system view, we see the camera, the NIC port, the computer, and the GPU. In the processing view, we see the camera, the rotary stage, a number of display tasks, a couple of ROI tasks, a task to create an image array, the AI anomaly detection task, and the I/O task for controlling the I/O card and LED. Back in the live view, we start the pipeline. With the pipeline running, we see the camera output, the ROI for the PCB under inspection, the ROI for the PCB detection results, the detection heat map showing location and intensity of the defects, and finally the image array for all 8 PCBs in a rotation showing their most recent results. Here is a portion of the code that makes up the anomaly detection plugin task, which, as with other plugins, is created using the Emergent eSDK Pro plugin API. Init and dinit API are run when starting and stopping the pipeline. The process API is run while the pipeline is running, and in this case is responsible for getting the image and running the AI prediction algorithm, and then setting a flag for another module to indicate action to be taken. Here is a portion of the code that makes up the Advantech control plugin task, which is responsible for taking the flag from the anomaly detection task and pulsing the LED on the defect PCB. Here is a portion of the code that makes up the Zaber control plugin task, which is responsible for configuring, homing, setting up triggering, and running the stage. And finally, if the application is to be run in eCapture Pro, then all of this is handled in the eCapture Pro UI via drag and drop processes with plugins compiled and loaded as DLLs. If running an eSDK Pro application, then you write this code to create and connect all of the tasks and to control the application either by your own UI, command line, or what have you. For this code, you would use the Emergent eSDK Pro API. What is now very old news? The new machine vision standard GigE Vision 3.0 has adopted RoCE v2 RDMA support, which now allows zero-copy transfers to system memory, thus equalizing performance with CoExpress and CameraLink HS, while allowing the use of lower-cost off-the-shelf NICs. Since Emergent has always provided zero-copy and more through our advanced and mature driver technologies, we naturally have adopted this standard, which can only strengthen our position in performance vision applications. To that end, Emergent has long released this edition with a simple firmware and software update with existing hardware, which was always RDMA ready. This includes all models in the Emergent portfolio, including our new Eros model. I do feel it is important to remind about the limitations of RoCE v2/RDMA compared to Emergent's mature solutions. The primary limitations are no multicasting support, which is a fundamental of Ethernet and streamed video technologies, no Windows support for Intel and Marvell NICs, no GPUDirect on Windows for NVIDIA GPUs. The last item about GPUDirect is very important and is a limitation of frame grabbers. Emergent, however, does have GPUDirect on Windows through our advanced and mature driver technologies. In contrast, the primary benefit of Emergent's advanced and mature driver technologies are listed below, which fill any gaps left by other vision standards, which essentially allows unparalleled flexibility. For the Vision 2026 trade show in Stuttgart this year, we are in the center of Hall 8 and looking forward to not one but 2 major product launches. I hope to see you all there. As you can see, Emergent has the highest performance camera and software portfolio all under one roof, and not via umpteen company acquisitions, and we keep our overall product portfolio focused. We innovate, design, develop, adapt, and expand the markets we enter, and have the foresight to do so. Please do contact us for further details, and we appreciate you taking the time to view our presentation.